Here's my thermometer showing an average room temperature. Now I'm going to dip this thermometer in some alcohol. Here's my alcohol from Target. So the temperature of the alcohol is about 68 degrees Fahrenheit. As I pull the thermometer out of the alcohol, we can see that the temperature starts to drop rather dramatically. This is due to the evaporation. This is due to the evaporation of the alcohol molecules off the end of the thermometer. So I'm going to try to explain how this works, why the temperature drops as molecules evaporate, using concepts of the Boltzmann distribution. This is a PhET simulation of phase changes. The pink circles in the middle will represent molecules, generic molecules, and you can see their motion is affected by the temperature, which I have control over. So at this point, fairly low level of motion, but if we increase the temperature, right now we're at a cold temperature, if we increase the temperature, then you'll see molecular motion increases, and we can start imagining a particular molecule getting enough energy to leave the pack, to break its bonds and leave the pack. There he goes, there he goes. That molecule has evaporated from the liquid state, taking with it a great deal of energy. It did return, and if it did return, then it brings the energy back to the liquid. But let's watch again. There's a few that have left. These would be the highest energy molecules in the population. They don't look like they're moving fast, but they broke their bonds, and that gave them potential energy. So they actually take with them a lot of energy when they leave the pack. I'm turning up the heat even more, and now you can see as the average energy increases, the chance that a particular molecule will have enough energy to leave the liquid is much higher. So it's much more probable that one of these molecules, by random collision, will get enough energy to leave the liquid. So now we have a fairly large gas population. Each one of those gas molecules has taken energy away from the liquid. I'm going to now use a mathematical model with human dollars to illustrate the idea of depleting the population of its wealth, its energy, by having the highest energy molecules leave the population. Here's a model for the loss of average energy due to evaporation. So here I've got a population of humans with some money, and I can total their money. And see, I have $1,130 total wealth divided by 11 people. So the average will just be $1,130 divided by 11, which gives me an average of $103 per person. All right, now let's imagine this number 11 here, the richest one, evaporates, leaves the population. Then I will have over here only 10 people. And now what is their average wealth? The total is now $250 less, and the average, it'll be divided over 10 persons instead of 11, but now the average wealth per person is only $88. This average here, that corresponds to temperature in molecules. So the average wealth would be comparable to average kinetic energy of molecules. That's what temperature measures. So you can see this is cooler due to loss of this highest energy individual, which would be the highest energy molecules, the ones that can break their bonds, the ones that can evaporate, leave the system. All right, now we're going to talk about larger populations here and get graphs. This should make sense to you. If we look at how much money do people make in the UK, this is England and Scotland and Wales. You can see there's an average. There's this kind of bell curve here, and most of the people are in this middle region right here. As we get to high incomes out here, the number of people or the percentage of the population that have these high incomes goes way down. This right here you can see is 1500 plus, so pay no attention to this. It's not meaningful. So this sort of distribution of wealth is very, very similar to the distribution of energies within a population of molecules. This graph here is called a Boltzmann distribution, and it's used to represent the velocities, which is related to the kinetic energies, of a population of molecules. And here we have different temperatures. We have 3 different temperatures on the graph. Okay, here's a graph showing the distribution of velocity, which is directly related to kinetic energy, versus N. N is the number of molecules. So just as we previously saw the graph of incomes in the United Kingdom and the y-axis was number of individuals, this is number of molecules. We have 3 different temperatures here. These are not well labeled, but these are temperatures. So you should see that we got a very cold temperature here. And at that cold temperature, minus 100 degrees C, most of the molecules have this sort of velocity range here, which for a molecule is relatively slow. As we raise the temperature, this is 20 degrees C, this is room temp, 20 degrees C. Then we see that the average molecular speed is now higher. It's in this range here. And if we get very hot, this is hotter than your oven at home, then we have the molecular distribution faster, average velocities. And you can see this tail goes way out here. This tail here goes way out, like so. All right. If we were to think about this in terms of our evaporation model, let's imagine that the threshold for evaporation is right about here. 1,000 meters per second. If you have that much energy, kinetic energy, then you can break free of the bonds. So you can see at 20 degrees C there are some molecules, a very small fraction of the total, very small percentage of the total, that could evaporate, break their bonds, go into the gas phase. At 600 degrees C, this blue line here, then a very large fraction of these molecules could break free. And that mirrors what we saw in the simulations, where at a lower temperature, there are a few that can be evaporating, but at a higher temperature, a much greater proportion of the molecules can do so. This is why it helps to warm up a liquid. If you're trying to evaporate it, warming it up helps tremendously. If we look at the red curve here, you can see that at this threshold velocity of 1,000 meters per second, there's essentially 0 molecules in the red curve that would have this energy, and therefore the evaporation rate at minus 100 degrees C would be almost no evaporation. All right, here's water at a relatively cold temperature. There are hydrogen bonds here, and the molecules are not able to leave their neighbors. Now I'll warm this. Okay, so now we're at 306 Kelvin. That is 32 degrees Celsius. So this is warm. You can see that one had enough energy to leave. We're well below the boiling point of water, but that one had enough energy to leave. What I'm about to say next may be difficult to understand, but if we had the blue graph and we didn't maintain its temperature, we just said let the molecules do whatever they do, if these molecules here were to evaporate, taking all their wealth with them, then the remainder here would rearrange to look very much like this green graph here. So the molecular distribution of energies would not stay in this pattern here, but would become a bell curve more like this pattern here. So the temperature would drop as the high energy molecules leave the system, evaporating. The average energy drops, and the curve, the Boltzmann distribution, will again be symmetric. Going back to the beginning, you can see the molecules that are attached to the thermometer are gradually losing their average kinetic energy because the highest energy molecules in that drop of liquid have gone into the air, leaving an impoverished population still in contact with the thermometer.